In this video, we will discuss economic models. Economic models is an abstraction or a simplification of real world. Real world is so complicated that to understand what things are going on in real world, we need to make a simplification. That's what we will find in economic models. For example, in this equation that we have here, it is an equation of total cost. The C here is total cost. The Q here is the output. In real world, total cost is influenced by many factors, not just quantity here, not just the quantity of output. There are many other factors. For example, whether or the behavior of the employees and still many other factors. But those complicated real world is simplified in a very simple model here that C is only influenced by quantity. This is not real world, but it is a rough representation of the actual economy, the actual world. Okay, let's see the next slide. There are many things that we can find in economic model or in mathematical model. The first thing that we're gonna see is variable. Again, back to this example, C here is a variable, Q here is a variable. So a variable, it is a value that varies. The value of Q can be 0, 1, 2, 3, so it varies. Okay, and the second thing is constant. This is an example of a constant in this example. 150 is always 150, so it is called constant because it is constant. Okay, and then we can also see perimeter. This is an example of perimeter. The 7 here in this equation is a perimeter. This perimeter will determine how the C is influenced by the quantity. Okay, so because it is positive, it is a plus here, so when quantity increases, the cost will also increase. So this is a parameter. It is a constant that is variable, or it is a coefficient that shows how the behavior of Q will influence the behavior of C. And also, a variable can be in the form of endogenous variable or with values originating from within. C here is endogenous variable because the value of C is originating from within this equation. The value of C is influenced by the constant and also the parameter and also Q as another variable in this equation. So it is an endogenous, while Q here is an exogenous variable because we cannot know how the variable Q here is determined. It is originating from something outside the equation, from outside the model. Okay, and in a more general form, this equation can be also written as C equals CO. So the CO here represents this constant 150, and the small c here represents the parameter, which is 7 in this equation. Okay, so this is a more general form of this cost model. Okay, let's see the next slide. There are 3 types of equations: definitional equation, behavioral equation, and equilibrium equation. Behavioral equation is something that we haven't discussed yet in this chapter, in this video, so we will discuss equilibrium equation later in detail, but let me discuss this in brief. That equilibrium equation is equation that describes the prerequisite for the attainment of equilibrium. For example, if it is about equilibrium of a market equilibrium, the prerequisite, the equilibrium equation is the quantity demanded equals the quantity supplied. We will discuss this later. What we need to discuss this at this step is that our example here is a behavioral equation. It is not a definitional equation. If it is a definitional equation, it is only about identity. It is only about definition. For example, in this example, profit is revenue minus cost. If revenue increases by 1, the profit will also increase exactly by 1. And if the cost here increases by 1, because the sign here is minus, so the profit will decrease exactly by 1 unit. So it is only a definition that total profit is revenue minus cost. It is different from a behavioral equation like the one in this example here. If the quantity increases by 1, the quantity will increase not by 1, but it will increase by 7 times 1. So the behavior of cost will influence, the behavior of the quantity will influence the cost, but not the same way as we find in this definitional equation. Okay, let's see the next slide. Our example here, C equals 150 plus 7Q, is a relation. It shows a relation of quantity and cost. And this relation can also be seen as pairs. There are two kinds of pairs here, unordered and ordered. If it is unordered, so the order does not matter. For example, A and B is the same as B and A. In this example, for x and y, 4x and 2y is the same as 2x and 4y. However, this is not the case in our example. 4q and 2 cost, for quantity and 2 cost is not the same as 2 quantity and 4 cost. It is completely different. So our relation here is not unordered, but it is ordered pairs, because for quantity and to cost is not the same as to quantity and for cost. Okay, let's proceed with the next slide. In the previous slide, we have discussed that this example is a relation. But this is not just any relation, because if it is a relation, just a relation in its broad meaning, when x value is given, it may not always be possible to determine a unique y value. But if it is a relation, as in this example, its value of q is in relation with a unique value of c. That is why it is called a function, not just any relation, but a function. But if it is a function, it is not necessarily the relation works to the other direction. It is not necessarily says that each value of c is in relation with a unique value of q. That's not the case for function. However, because our example here is very simple, it is a linear equation, it also works to the other direction. I mean, it is not just Q has a unique value of C, but C has a unique value of Q because it is a linear equation. However, in later chapters, we will see that if we have a more complicated equation, like if it is if the cost function is a quadratic equation, it is not a mapping. A mapping is a relation when each x value always determines a unique y value, and at the same time each y value has a unique x value, so it works in both directions. This is not the case for function. Okay, it is a function, our example here. It is also a mapping, but if we have a more complicated equation, we will see in later chapters that this cost function is not a mapping. However, in this example, it is also a mapping. Two more things that are listed here is domain and range. Domain is the set of all permissible values that x can take. For example, the domain is about the q here. For example, q is a quantity. You know, quantity is not relevant to be negative. So I can say that in this example, the domain for q is positive values. So it is from 0 to 1, 3, 4, 5, 6, and so on. So positive values are the domain for the quantity here in our example. Okay. And also we see range here. Range is the values, all set of values for the C here, for the cost here. Because in this example, C is cost, and cost is not not relevant to be negative. So I can say that the range for C is all positive values. Okay, that's for this slide, and let's proceed to the next slide. This is the example that we've been talking about through the previous slides. This is about cost. C is the total cost per day, and Q is output per day. And the domain, I have discussed this, that it is in this example from 0 to 100. So it makes the cost from this cost equation. It is from 150 to 850. Okay, let's see the next slide. This slide is about types of function. There are many types of function. The first function listed here is a constant function. A constant function is a function which is constant. For like this example, y equals 7. 7 is always 7, so that is why it is called a constant function. The next type of function listed here is polynomial function. The general form of a polynomial function can be expressed as this equation: y equals a0 x to the power of 0 plus a1 times x to the 1 plus a2 times x squared plus, and so on until the last element, which is represented here by an times x to the nth. This equation expresses a general form of polynomial function. Perhaps it can be clearer if we start to discuss some types of polynomial functions. Okay, if the n here if the highest degree of the x, or the highest exponent of x is 0, so it is 0 here, what we will find is a constant, because you see any number to the power of 0 will be equal to 1. Here, our example in the constant function here, 7 times x to the power of 0 here is the same as 7, because x to the power of 0 is 1. So the exponential function in this first type, when the exponent is 0, is the same as a constant. And then next, if the exponent is 1, or the n here is 1, what we will find is a linear function, linear equation like this one. The q here is to the power of 1. So c equals 150 plus 7 q to the power of 1 here. The exponent here is 1. So the first degree of polynomial function is basically a linear function, like the example that we have discussed so far here. And we also know from our previous courses in mathematics that for a linear function, the shape of the line, the shape of the diagram that we can find for this linear function is a straight line. Not just any line, but a straight line. If it is a straight line, we can find that the 150 here in this equation is the vertical intercept, or the A0 here is the vertical intercept, because when the quantity is 0, the c will be 150. And normally in mathematics, if the c here is the endogenous variable, it will be placed on the vertical axis, and the q here will be placed on the horizontal axis. So the 150 here will be the vertical intercept. Okay, the quantity of c when the total cost when the quantity here is 0. And then we can also see here slope. The 7 here is the slope of this equation. It shows the steepness of the graph of this equation. Mathematically, it can be expressed as the change in y divided by a change in x, or in this example, a change in c divided by a change in q. Okay, for example, if q increases by 1, that's a change in q, the c will increase by 7. So the slope is 7 divided by 1. That's the slope, that's 7. Okay, the change in c is 7, the change in the quantity is 1. So 7 divided by 1 is 7. That's the slope. In this example, we have a positive slope. Okay, so it will make the graph an upward sloping graph. It moves from lower left to upper right. It is an increasing graph. Okay, so it is called upward sloping. If the sign here is negative, so what we will find as the graph is a downward sloping graph. So it is a graph which is started from the upper left of the diagram and then it moves down. Okay. Next is second degree polynomial function. So the exponent here is 2. If the exponent is 2 here, so the exponent of the x is 2. So we have a quadratic function. So x is squared. So we have a quadratic function. If it is a quadratic function, the type of the graph that we're going to find is a parabola. If it is a parabola, so it can be either a graph like a valley with a minimum point, or it can be like a hill which has a maximum. So if it is if the A2 here, the coefficient here is positive, we're going to find a valley. First, it will be a decreasing graph, and then reaching a minimum, and then after the minimum it will go up. And when the A2 is negative, we're going to find a hill, increasing, maximum, then decreasing. Okay, and then if the exponent is 3, here the exponent of the x is 3, the highest exponent is 3, we're going to find a third degree polynomial function, or a cubic function. If it is a cubic function, we're going to find a little bit more complicated graph, which for example, it can first the graph will first an increasing graph, increasing, and then reaching a maximum, decreasing, reaching a minimum, and then afterward it will increase again. Or it can start with a decreasing function, and then minimum, increasing, maximum, and then decreasing. Okay, don't worry about this detail of this cubic and the quadratic function, because we will discuss this later in our next sessions or videos. Okay, let's see the next slide. The next function discussed in this slide is rational function. Rational function is a ratio of two polynomial functions. For example, this is a very simple example of rational function. It is a ratio of a and x. Remember that if a polynomial function, if the degree of polynomial function is 0, we're going to have a constant like this one. It is a constant of a. And it is also a polynomial function. The exponent here is 1. So it is a first degree polynomial function. So this rational function is a ratio of a over x. The a is polynomial, the x is also a polynomial. And in this polynomial function of a over x, if the value of x increases, the y here, a over x, will decrease. If the x becomes very large, the y here will become very small. So the graph here will always decreasing, and then if the x here is very large, it will approach 0. It will be very small that it approaches 0, but it will never become 0. So the graph here will always approach the horizontal axis, but it will never touch the horizontal axis. That is why this horizontal axis in this example is the horizontal asymptote. The same thing for the vertical axis here, because if x decreases and then it becomes very small, so x goes here to the left, x becomes very small, the value of y here will become very large. So the graph here will always approach the vertical axis, but it will never touch the vertical axis. That is why the vertical axis here, the y-axis here, is called the vertical asymptote. That's a rational function. Next is we will also in later session discuss non-algebraic function. The non-algebraic function that we will discuss is exponential and logarithmic function. Okay, at the moment we will not discuss further about this non-algebraic function because we will discuss this later in other videos. Okay, and another explanation for function is that sometimes certain type of functions can be easily described using visual explanation like this one. Okay, if the variables that we have is only two, like in the example of cost, the variables are only cost and quantity, we're going to have a two-dimensional space. The first space is for the cost at the vertical axis, and the second space is for the horizontal axis, which is the quantity. But we can also add one more space, add one more variable here. So in this example, we have three-dimensional space. Z equals is a function of x and y. So we have z, x, and y. So we have three dimensions. And if it is in three-dimensional space, we're going to have z here as the height and y as the length, and also x here is expressed as the depth of this three-dimensional space. However, when we have more than more complicated than three-dimensional space, like for example we have 4 dimensions, 5 dimensions, it is very difficult to express this equation in visual illustration like this one. Okay, when we have more than 3 dimensions, usually it is only described in mathematical equations. Okay, like this one, for example, z in this example is influenced by x, by y, and by u. It is very difficult for us to express this in visual dimensions like this one. Okay, now let's see exercise. Okay, this is the exercise for the topic that we have discussed today. The same equation here, C equals 150 plus 7Q. C is total cost per day and Q is output per day. And the maximum output that is determined by this exercise is 100 units. So the output cannot be any larger than 100 units. So because we know that quantity is not relevant to be negative, so we can say that the domain is started from 0 and it stops at 100 because it's already been stated here that the highest value of the output is 100. And the range of this equation, we have discussed this range, is from 100 and is from 150, because when the quantity is 0 here, the C is 150, and then when the Q is 100, C is 850. And then we are supposed to draw the sketch of this graph. Okay, let's see the next slide that will tell us how to put this equation, this functional equation, into a graph, because we have Q here. The Q here is the power of the Q is 1 here, so it is a linear. So we can expect that we're going to find a linear, a straight line. The vertical intercept is 150 and the slope is 7. Let's see here. Okay, this is the equation that we're gonna try to find the graph. First, this is the vertical axis. The vertical axis will be for the cost, the total cost here. So this is the C, and then this is the 0. Remember that the domain starts from 0. The range will start from 150. Here, any values lower than 0 is not relevant because the range has been found in the previous calculation that it starts from 150, and also I think we can agree that if the total cost is less than 0, that's not too relevant. So I make the line here rather different. It is made in dashed line to show that it is not relevant. It is irrelevant. Okay. And the horizontal axis is for the Q. Horizontal axis for the Q. Yeah, the Q. The same thing for Q is that because Q is not relevant to be negative, so the line here is made in dashed line to show that it is not relevant. Okay. And then we know that the domain is from 0 to 100. So we are not supposed to draw the line any larger for the quantity any larger than 100. So it is only from 0 to 100 because it's been stated in the exercise that Q cannot be any larger than 100. And then when the Q is 0, the total cost is 150. So 150 is here. And also, we know that when the quantity is 100, the cost is 850. So we can also find another point is that if the quantity is 100, the C is 850. So we have found 2 points. Here, this point and this point here, and we only need 2 points to draw a straight line. We know that this is a linear function because this is a first degree polynomial function. The exponent here is 1. So from the previous slide we know that it will create a linear function, and the shape of the line is a straight line. So by finding 2 points are just enough to draw a straight line. What we need to do next is only connecting these lines from this to this one. So this is the curve. This is the C equals 150 plus 7Q. However, to show a more comprehensive understanding about our curve, even though this is not so relevant in this example, I also show that when the cost is 0, when the cost here, total cost here is 0, the Q will be 150 divided by 7, which is minus 21.4. So this is the quantity when cost is 0. So this line can be extended here to negative values of C and Q here, which is irrelevant. That is why it is made in dashed line again. And actually the answer is not this dashed line, but this solid line. Okay, this is the answer for our exercise, which is C equals 150 plus 7Q. Okay, I think that's the end of our slide. Thank you, and I hope it can give you better understanding of these economic models, the basic things about economic models in mathematics for economics and business. Thank you.